Okay, well, grade nines, it's been so long since we've spoken like this, okay, to each other. So, listen, um, yeah, we're going to go back to doing these Zoom lesson. All right, well, here, a little taste of grade 10 science for you, okay? Um, Here's the light and optics unit, okay, that we normally do in grade 10. And I just for interest's sake, I posted the chemistry. The chemistry is a lot of repeat of grade 9, except you just go into more detail. And there's some new things like acid and base chemistry and balancing chemical equations and so on. Then there's this unit on biology where you talk about cells and everything else. Cells and organ systems and everything. But you picked optics, so yes, good choice. That's a great choice. After all, it's physics. So, all right. So anyway, I gave you a bunch of handouts yesterday. And today we're going to look at some of that and do a couple of like little activities. And so let's see how much of this we can do in one day. We're just going to do the law of reflection, okay, on what light is today. Okay, so these first couple things. Don't worry about this textbook homework for now. Okay, don't do it. That it's not in the grade 11 textbook or anything. So just leave it. Okay, so ignore this. Here, let me do it in a better color maybe. Ignore that. Okay, ignore this text here, just the textbook. Do this though, that's good. Okay, ignore this textbook homework, but do the little activity sheet that I'm giving you for sure. Now the mirrors, that's for tomorrow. Okay, so don't worry about the curved mirrors. We're not doing that today. Okay, so here's the deal. Yeah, let's take a look at the sheets I gave you, because they're a beautiful thing to behold, really. Okay, now here, take a look at this. You've got sheet number 1, the nature of light, okay? Now, here's this big question in science. I love this question. It's kind of a cool and amazing thing. What is light? Now, the answer to that question turns out to be a real brain teaser, okay? But for centuries, people have been wondering what light really is. So let's go back to the late 1600s. This is the time of Sir Isaac Newton. Okay, and Sir Isaac Newton at the time, when he was very young, had already come up with his theory on gravitation. Okay, so he was considered one of the world's greatest geniuses, sort of like the way Einstein would have been considered in his time. Okay, just a household name. Everyone knew Isaac Newton was a smart man. Okay, so they came to him and they said, listen, you're such a great intellect, why don't you come up with something, a good theory for light? And so he took a shot at it, okay? Now, Newton proposed what is called a particle model for light. Whoops. I'm sorry, these pens are a little too thick. Let me see if I can fix that. So he proposed something called a particle. Oh, it's really acting up. Let's see. A particle, there, that's better, theory. Oh, now it's acting up again. It's odd, it's not doing, yeah, let's see if I can fix it. Better, okay. Particle theory. So, in other words, when we hit you with a beam of light, we're hitting you with a stream of particles, kind of like the way I hit you with a super soaker. Not the gun, I hit you with the water stream, okay? The stream of water would be a stream of water molecules, right? That's hitting you there in that case. So Newton had this idea that that's what light is. It's a beam of particles. And it was called, he called these particles corpuscles. So it was called, wow, the palm rejection is not good. The corpuscular theory. Okay? And that's it. Now you can fill this out as we go along here. Now this other guy, Christian Huygens. Okay, Christian Huygens, you probably never heard of him. That's how you spell his last name. You see his name is, first name is Christian. Okay, so Christian Huygens, you see his name up here. So Christian Huygens proposed a wave theory. Okay, now you probably never heard of him. Not as famous as Isaac Newton. Okay, but that was his idea. That in other words, light was a wave, and he used this theory to explain a variety of phenomena. Okay. Now, these two theories made some opposing predictions. For example, Newton predicted, okay, that light would speed up, okay, when entering more dense media, like glass or water, okay, from air. But Huygens predicted that light would slow down. Now, the reasons they made these opposite predictions are basically like this. Light, when it enters glass from air to glass, let's say it bends. Okay, that's called refraction. We'll talk about that later. So light refracts when it enters the air, it bends. Okay, and the way that it bends is if a wave were to bend that way, it only bends like that when it's slowing down. And that's why Huygens made that prediction, because other types of waves, like water waves, they bend the same way, but only when they slow down. Okay. Newton, though, he had this gravitational idea why they would speed up, that they were the light particles were gravitationally attracted to the glass or to the water, and they would speed up as they entered from this force of gravity. And so that was his idea. Now the key is they make opposite predictions. Somebody has to be wrong about this, right? Somebody's right and somebody's wrong. Okay, or maybe they're both wrong. Maybe light doesn't change speeds at all. But, you know, so there's only, you know, a couple of possibilities here. Either one of them, you know, they can't both be right, that's for sure, because they're making opposite predictions. Anyway, this is important. Newton's theory was taught in school for at least 150 years. Now, this was without experimental evidence. So 150 years, guys. That's a long time. Well, maybe not quite that long, actually. Maybe more like on the order of about 100 years or so. But anyway, a pretty long time, okay, to be teaching something in school, until discoveries in the early to mid 1800s. Okay. Okay, these discoveries, this is my idea of a sense of humor. They shed some light on the situation. Ha. Please write that down in your notes, because you know what? It's worth writing down. Anyway, first Thomas Young, this guy named Thomas Young, was first to confirm the phenomenon of interference. Okay? Having a really hard time with my pen on the screen today. Okay, interference. Okay. Yeah, I meant to say, okay, I'm sorry, let me rephrase it. I meant to say double slit interference. That's why there's 3 words here. It's been a while since I've taught grade 10, so like I've got to get used to my notes again. Anyway, second, other scientists confirmed that light actually travels slower in the more dense media. And so Huygens was right. Only waves can have interference. Remember we talked about nodes and antinodes? So this thing, interference, you can't have a beam of particles and that beam shows interference. It doesn't make sense. Like, there's no waves there. There has to be waves to have interference. You have to have crests and troughs, or compressions and rarefactions, or whatever kind of wave it is. You have to have a disturbance like that, though, to get interference. Remember, interference is this property where waves pass through each other, and you get like super crests and super troughs and stuff like that. Only waves can do that. Particles don't pass through each other like this. They collide, and you know, imagine 2 streams of water intersecting. It would just splash all over the place. You wouldn't get interference. That wouldn't make sense. Okay. So anyway, it turns out Huygens was right. So they taught Newton's theory for 100 years in school, but he wasn't really correct. But they went with the more famous person, which is not the way science is supposed to work. You know, unfortunately for Huygens, he never lived to see his theory adopted. I mean, neither one of them did. It was 100 years later. But yeah, Huygens was right, and interference was a big deal. When Thomas Young did that experiment, that was the famous experiment in physics that we talk more about in grade 12. All right, so here's the good news for you. You already know the properties of waves because we did the sound unit already. So you're experts at waves, right? So look at this. These are characteristics of light waves, or any type of wave. Light waves are transverse, so they have crests and troughs, not like sound, which has compressions and rarefactions. These are transverse waves this time. Okay, I'll explain another time how we know that. But anyway, here you have a crest, right here, a trough right here. A wavelength goes from trough to trough or crest to crest, of course. Amplitude is measured from the what's called the equilibrium, okay, position of, in the case of light, it's of the electric field, okay? And that's it. So here you have your basic characteristics of the wave. We also have the universal wave equation, which we did in the sound unit also. Isn't this wonderful? So speed equals distance over time. That's a famous formula. It goes with any moving disturbance like a wave, which is equal to wavelength over period, or frequency times wavelength. So here is in a nutshell, okay, the way we write that, and that is the universal wave equation. You also know that frequency is the reciprocal of period. We did that when we did sound also. So moving right along, guys. Whew, you guys are amazing. All right, now let's come to like what physically light is. Scientists working with electricity discovered a connection between electricity and electricity. Wow. It's so annoying today. And magnetism. Okay, there's a connection between those two things. That's what we call electromagnetism. They discovered that light is actually a self-propagating disturbance in an electric field. Now, you don't really need to know all this, but we'll save it for grade 12. But when we talk about what light is, it's called the wave theory on light. It's a self-propagating disturbance in an electric field, okay, that surrounds charged particles. So light actually comes from charged particles, like electrons, that are moving or accelerating. These particles will release light whenever they move. Okay, and that's the deal. So charged particles are surrounded by something called an electric field, and that electric field moves, like it changes when the particles accelerate or move. And so when they move moving around, their field changes around them, and it's that change in their field that creates the wave. Okay. Now, a famous scientist named Heinrich Hertz was able to produce light that you cannot see with your eye. Okay. Okay, that are now called radio waves. So he produced for the very first time radio waves. And radio waves are light also, but it's light that you cannot see. And you can thank these guys for the word I want you to write here is annoying, cell phones. Okay, so please write that down for a mark. Okay, annoying. Actually, it's not so much the cell phone, it's annoying. It's just you guys are annoying when you use it, that's all, right? So scientists have since discovered a broad spectrum of electromagnetic waves. The properties of the light waves vary according to their wavelength. All right, so let's take a look at the spectrum of light. Now, I think we looked at this before, but when we did science, like back in the space unit, but let's just take a close look at it here. So going from long wavelengths to short wavelengths, radio waves here have wavelengths in the kilometers in size, down to hundreds of meters. Okay, actually right down to meters and centimeters. So those would all be considered radio waves. Your cell phones are like millimeter, centimeter, millimeter waves, okay, for wavelengths. They're still radio waves. Now, in like smaller than that, centimeters, I guess, actually no, I'd say your cell phones are maybe tens of centimeters or down to maybe meters in wavelength. Now, microwave radiation is in centimeters, so they're like centimeter or millimeter waves, okay? And infrared light, infra means before red, that has wavelengths in the 1,000 nanometer range, okay, approximately. down to like, so 11, 1200, 1300 nanometers, down to about 800 nanometers would be infrared. Now, visible wavelengths, this is really interesting. The colors of the rainbow, and I'm going to get rid of indigo, it shouldn't be there. But anyway, the colors of the rainbow here, the wavelengths range from approximately, and this is a very interesting fact, they range from about 800 nanometers for red down to about 300 nanometers for violet. Okay, so nano is a billionth of a meter. So very, very small wavelengths. That's all you can see. Okay, so there's a tiny little band of wavelengths in here. That's all you can see. Okay, green is right in the middle at around 500 nanometers. All right, beyond violet is ultraviolet, and literally ultra means beyond. So beyond violet is ultraviolet. That has wavelengths down from 300 nanometers down to about 100 nanometers or so. Shorter than that, we get X-rays. Okay, and then shorter than X-rays, we get gamma rays. So these comprise a range of wavelengths. Anything shorter than about 10 to the minus 10 meters. So in other words, anything shorter than about 0.1 nanometers would be considered a gamma ray. Okay? And by the way, it starts becoming harmful right in the ultraviolet range, and anything past that is even worse. Okay? We call that ionizing radiation. That's why you get sunburns from ultraviolet light, but X-rays and gamma rays would be even worse, of course. But the sun doesn't emit X-rays and gamma rays. Thank heavens for that. Okay? Now, visible light only represents a tiny fraction of the full spectrum. Okay, ranging, I'm going to say 800, I'm going to correct that. 800 nanometers for red wavelengths, and then down to about 300 nanometers for violet. Okay, 1 nanometer is 10 to the minus 9 meters, so that's a billionth of a meter. So these are very, very short, small quantities. Infra means before, I said that already. Okay, our visible light of longer wavelengths. Okay, then red. Ultra means beyond. Okay, thus ultraviolet waves are invisible waves of shorter wavelengths than violet. Everything, now by the way, ultraviolet we use the acronym UV, and infrared we use IR. Okay, so I'm going to highlight those. UV for ultraviolet, IR. Okay, for infrared. Now everything UV and beyond, no, I should say and shorter, in wavelength is toxic for reasons the wave theory cannot explain. Yeah, in fact, this was a real mind bender. Ultraviolet light, for whatever reason, starts becoming dangerous. Okay, and anything shorter in wavelength is even more dangerous, and for a while we couldn't understand why. And the reason why we couldn't understand it is because light is behaving in a very bizarre fashion. Okay, and under some circumstances where it just doesn't behave like a wave. Okay. Now, here's the deal. Electromagnetic wave theory changed the world. It allowed for the invention of radios, cell phones, motors, generators, and many other technologies. Think of the world without that list of items, just right there. Okay? Arguably, without cell phones, the world would be a better place, but without generators for electricity, okay, stuff like that. These are things now that are just an integral part of our society, right? So that's, the wave theory made all of that possible. The engineers discovered this technology, okay, that they could construct based on the science of the wave theory. Now, by the way, speed of light. Scientists confirmed that the speed of light in a vacuum is 3.0 times 10 to the 8 meters per second. And this is as fast, this is the fastest speed, okay, that light has. If it's in glass or water, it slows down slightly. Okay, but it's fastest in a vacuum when it's not encumbered by the presence of matter. Now, by the turn of the 20th century, scientists like Einstein, okay, were trying to use the wave theory to explain how matter, or atoms I should say, absorb and emit light. Unfortunately, their observations and experiments led to an inescapable conclusion. When sometimes light basically behaves like a particle that they called a quanta. This is where quantum theory comes from. Later called a photon, okay, and not a wave at all. This was considered a catastrophe, okay, for the wave theory. Now, for example, even trace amounts of ultraviolet light, X-ray, and gamma can cause cancer. No amount of visible light can do that. Why? Because ultraviolet photons carry enough energy to break chemical bonds. We call this radiation ionizing. Radiation is extremely dangerous. Thankfully, X-rays and gamma rays do not occur naturally here on Earth. And so it's only us that can make this possible. Okay, but that's it. All right. Anyway, light is long story short, light is a bizarre thing. Okay. It has kind of a dual nature. Sometimes it behaves like a wave and sometimes it doesn't. And what we're faced with today, this puzzle is 100 years old. We're faced with this problem today that, look, in certain experiments we just use a particle theory, and in other experiments we'll just use a wave theory. And it works. Unfortunately, we don't understand how it's able to have two natures. Okay? It never displays them simultaneously, though. It's always one or the other, depending on the experiment. All right, recall the Rutherford-Bohr model of the atom. How do atoms emit light? Okay, so electrons occupy what Bohr called, let's call them shells or orbitals, okay, surrounding the nucleus. Now, remember how there's 2 electrons that go in the first orbit, and then up to 8 in the second, and 8 in the third, and then 32 in the fourth, and so on. Okay, so these are called orbital shells, or just shells, or just orbitals sometimes. Okay, but they're not really orbiting the electrons; they're just sitting there. Okay, and these we call harmonic modes. But anyway, how does an atom release light? An atom gets excited, okay, by heat or light or by some other energy source. Okay? What happens when atoms enter an excited state is electrons jump to higher shells. Okay? And the atom is in an excited state. Now, when the electrons in the unstable excited state jump back down, okay, to their shell, okay, to their normal shell, I don't know what this is, okay, and in the process give off a photon. And that's how atoms emit light. They emit light in the form of photons, and they do it, electrons will do it, when they get promoted to higher levels and fall back down to their original level, okay, and when they do that, you get light being produced in the form of a little particle of light called a photon. Okay. Now, because atoms emit light like this, the colors they give off depends on the energy change, okay, of the electrons. So this diagram shows red and green spectral lines coming from nitrogen and oxygen atoms. Okay, so here, if you want to look at this, if the electron falls from the third orbit down into the second, red light is given off. If it falls from the fourth level down to the second, green light is given off, and that's what you see here. So the color that they give off, the color of the photon they give off, depends on how much change in energy there is when they are falling back down from their promoted state. Like, an electron gets promoted up in here somewhere and it belongs in the second orbit, it's going to make its way back down there, and when it does that, it'll release a particle of light called a photon. Depending on how far it goes, that will determine the color of the photon. Okay. Anyway, there's lines that call the spectrograph spectrum of radiation, right? Like coming from an atom, like the sun gets the full rainbow, but individual atoms can have certain like line spectra, it's called, but they'll learn about that in grade 10, okay? Or grade 11, pardon me. So we won't spend too much time on it here. Now, atoms that emit their own light are called luminous. Okay? Atoms that reflect light from other sources are called non-luminous. Now, what luminous objects glow in the dark? Okay? They glow in the dark. These ones only reflect light. And so, like, if you look around your bedroom, okay, if you're looking at this on a computer screen, which you obviously would be, the computer screen is emitting its own light. You can turn out all the lights and still see the computer screen because it emits its own light. And that is a luminous object. Okay, light bulbs are luminous when they're turned on. The table, though, like I'm sitting at a table right now, sitting in a chair and holding my my pen, okay, that I'm using to write on the screen. All of those objects are non-luminous. If I were to turn out the lights, I wouldn't see them at all. Okay. All right. So atoms can be excited to emit light in a number of ways, depending on how they're being excited. Okay. Now, if they're excited by a chemical reaction, we call it chemiluminescence. Okay, so this is a chemical reaction. Whoops. Okay, so this is a chemical reaction. Causing atoms to release light. Okay, now I'm not going to write the whole sentence because it's a bit annoying. The way my laptop is responding here today. So bioluminescence is again a chemical reaction, okay, occurring inside living things. So some living things can emit their own light. Not humans, of course. We don't glow, okay? But there are things called glowworms. Okay, things called glowworms. There are things called fireflies, okay, that we would have in our neighborhoods around here. There are various other, there's types of things that float in the ocean that can also emit their own light, like that anglerfish that has the glowing lure, okay, and it lives like deep in the deep oceans where there's no natural light, and it uses this glowing lure to lure in its prey, okay, and maybe you saw that on like Finding Nemo or whatever. Yeah, that's a real thing. So there are various organisms that are able to emit their own light. The most common one for us would be a firefly, okay. Electroluminescence is when you use electricity to create light. So you stimulate the atoms with electrical current and they release light. Triboluminescence is when you have you put pressure on a crystal, okay, to release light. You just got to excite the atoms, right? That's our goal here. Excite the atoms. Once they get into an excited state, they'll release light. There's different ways of exciting them, so that's what we're looking at now. One is by chemical reaction, and that could occur in just a regular chemical like a glow stick, okay? And it could also occur in a living thing like a firefly, okay? So that's chemiluminescence and bioluminescence. They're really both chemi, right? It's just that chemical reactions that occur in a living thing, we call it bioluminescence. Now, electroluminescence is when we use electricity, okay, and we pass it through something to create light, okay? So electricity passing through things can make them glow, okay, and that is called electroluminescence. Triboluminescence, if you put pressure on a crystal. So certain crystals, when you squeeze them, they glow. Like if you chew on a winter mint like Lifesaver, And if you do it in pitch dark, just as you're biting into the crystal, there's a little flash of light. Okay, it's really hard to see it. But yeah, that's called triboluminescence. Now, fluorescence, okay, fluorescence is when atoms absorb light of one color, usually UV, ultraviolet, and then emit another color. In other words, they get stimulated by ultraviolet light, and then they emit other colors. So if you've been to a place that has, like, let's say you go to Flying Squirrel, and they do the night one with the ultraviolet lights, so they turn off the main lights, and then they turn on these ultraviolet lights, okay, and then your white shirt and stuff will glow. I have a demo that I'll show you next time I see you guys in class. Phosphorescence. Phosphorescence is when you have phosphors that glow. Okay. Yeah. Anyway. Actually, here. You know what? The best example of phosphorescence. Here's where it's similar to fluorescence, except it's slow. Fluorescence is basically instantaneous. Okay. Glow-in-the-dark silly putty. Okay. Or glow-in-the-dark stickers. So I'm just going to write glow-in-the-dark paint. Okay. Etc. What happens is absorbs visible light when it's exposed, and then slowly releases by glowing over a long period of time. So those, like, you know, some people have them stuck to their ceiling. They look like little stars when you turn out your bedroom lights. Okay, glow-in-the-dark stickers, glow-in-the-dark, anything that's glow-in-the-dark except for glow sticks. Glow sticks are chemiluminescence because you're mixing two chemicals there. Phosphorescence, though, you sit the stuff under a light. It absorbs some of that energy and it slowly releases it. That's called phosphorescence. Incandescent is when something gets hot. Okay, so like a red hot coal will glow. Okay, a fire glows for this reason, a candle. So fire, candles, you know, a stove, element. These things glow because of incandescence. That word comes from candles. Okay, so hot objects, you stimulate something with heat, and if it gets hot enough, it'll glow in with light, visible light. Also, there's infrared, but yeah. All right, I'm going to let you answer these questions. So there's no textbook homework. So please just give these questions a shot. It's pretty straightforward. No problem. I'm going to let you do it. I included a little handy metric system. You don't really need that for this exercise. Okay, but there you go. Okay, so a few questions for you to answer in the homework. Nothing from a textbook, though. Just do it right there. Okay, I got one more thing for you. And this one won't take very long. Law of reflection. Okay, very simple. The angle, like when something bounces, when light bounces off of a mirror or something like that, the angle of incidence, that means the angle of the light coming in equals the angle of reflection. And that's it. That's the law of reflection. So here, I want to show you how we measure these angles. This angle here that we've labeled theta, okay, it's a Greek letter, and I'm sorry you're not used to it, probably, okay, in grade 9, but theta I stands for the angle of incidence. And we measure the angle of incidence from a normal line that is perpendicular here to the surface of the mirror. So here there's this 90-degree angle. This, in math, we say anything that's perpendicular is normal. Okay? Normal means perpendicular. So the incident ray, the angle of incidence is measured from the dotted normal line, okay, down the middle. I'll color the normal line red. That red line is the normal line. Okay, and then the angle of reflection is also measured from the normal line. Now these two angles are equal. Okay, and they look equal in the diagram. That's on purpose. That's how light reflects. Okay, now there's a really cool word called specular. Okay, a specular reflection occurs off of a very flat surface. So a flat surface or plane surface that's smooth will reflect all the incident rays according to the law of reflection, of course. But the thing is, because the surface is flat, you get a very sort of, because the rays are coming off parallel, you get images, okay, that form in the reflection. So for example, oh yeah, this is called specular. I don't know why I was confused there for a second. I guess I didn't write the word specular yet in the paragraph. So this is called specular reflection. Now I've got a little picture of that here. See, if light is reflecting off this nice and flat surface down here, okay, that I'm making a scribbly line over it, and all the light bounces off in the same direction, that's called a specular reflection. And it happens because, pardon me, the surfaces are flat, okay? Now, a diffuse reflection happens when the surface is rough. So a picture like your skin, for example. You can't see your reflection in your skin because even though I'm sure your skin is beautiful and smooth, okay? However, on the microscopic level, if we were to zoom in on your skin, we would see that is not so smooth, okay? Now maybe it feels smooth to the touch and it looks smooth to your eye, but zoom in on that with a powerful enough microscope and you'll see that it is like an alien landscape with all these pores and, you know, mountain ranges and everything in them, okay? And that's it. So that skin gives a diffuse reflection. That's why you can't see your reflection in the palm of your hand or in the back of your hand or something, or in a wooden table. But if we put a polish on the table or a finish, like a varathane finish, and that forms a smooth layer, we can get a specular reflection. So a polished floor, you can see your reflection in it, like say the gym floor in our school, the wood floor, okay? Or a tiled floor that's been waxed, okay? The wax can make it a smooth surface and give you a specular reflection. You can see the reflection of people in it or objects in it. Whereas a diffuse reflection, like the clothes that you're wearing, don't give a regular reflection. They're rough surfaces. So like what happens is you get some light being reflected, but it's diffuse reflection, and that's it. Okay, it's still obeying the law of reflection, by the way. It's just that wherever the light hits, you get all these different angles, okay, of reflection that's possible. So it scatters the light. Okay, glare is created on a road. On asphalt, when the asphalt is not a smooth surface, it's very rough, so this is what we drive our cars on. We want it rough for friction, okay, so we can drive our cars properly and control our cars. We don't want the floor to be slippery, okay? Now, if it rains, the rain will fill in all the irregularities in the road surface and form a smooth layer of water, and then you can see a reflection in it. If the sun shines off of that layer of water, the reflection into everyone's face who's driving, okay, on that road can be quite distracting. And so, yeah, we try to keep the roads dry for that reason, have drainage so that puddles don't form on the road that give specular reflections like that. Okay, so now, normally, the asphalt is prone to diffuse reflection. Okay? However, okay, when it's wet, you get specular reflection. Okay, and that's it. And here I've got a picture of that there for you. How asphalt normally looks like this one, But you see what happens when there's water sitting in it, fills in all the rough irregularities, and then you get a specular reflection, and then that is going to be very bright in your face. All right, one topic left. How do images form in a plane mirror? Now, plane doesn't mean like it's not chocolate covered or anything like that. Like it's not like a plain donut. A plane mirror means a flat, perfectly flat mirror. Okay, plane means flat in this case, in this context. Now, I wrote here, actually, I don't know why, I forgot to change it. Okay, this I meant to say for Bridget. Okay. The rays are coming from this image of, it's not Steve, but you know, we can call Robin Steve maybe. I don't know, we can call Bridget Drew. I mean, that's Marin's brother, but like from some time ago. Okay. This image of Robin. I changed it everywhere else. I forgot to change it there. But there you go, I fixed it. Okay, now it says here, we can see that these rays obey the laws of reflection. So here's how you see an image. So like I just want to show you the mirror is on this side. So this is really Robin. This is the real Robin on that side, okay? And she's looking, here she is. There you are, Robin, okay? And you've got this ray of light. We can all see your nose. Don't worry, you have a very lovely nose, okay? So don't be shy or anything like that. I'm not trying to, you know, make you feel bad or anything, okay? But we see your nose because light shines off of it. Otherwise we wouldn't see it, right? So right now there's light shining off of this nose here. That light comes from your nose, hits the mirror, okay? And then it reflects into Bridget's eye. Okay? So here Bridget is looking at Robin's reflection. I mean, Bridget, you should really not be rude and actually turn and look at it, but whatever, it's going in her eye. Okay? And here we see the angle of incidence equals the angle of reflection, so that's normal. Okay, that's how that must happen. But here's the thing. From Bridget's perspective, the image of Robin in the flat mirror here is actually over here. Okay? So let me get that with the highlighter. It's over there. That is the virtual image of her. That she looks like she's in the mirror or behind the mirror. Now notice there's an inversion. Like so, you know, if you look at Robin's face outside the mirror, she's kind of like turning towards her left, but her mirror image is turning towards her right. Okay? And so like, well, actually, no, I've got that backwards. No, the mirror image is turning towards her right. That's right. And she's actually turning sort of towards her left. So in other words, her sort of cheek is leaning on, whoops, I didn't mean to do that. On this side here, that's her left side. But here, it's turned around. Okay? So what's happening is we're seeing the mirror image inverted laterally, okay, in this mirror. And that's it. Okay, so anyway, you'll notice that this distance also, so if I were to zoom in on this distance from here to here is the same as the distance from here to here. Okay, it's the same distance. So when you're looking in a flat mirror, you look at your virtual image of you, and it looks like it's behind the mirror. And that's how the reflections work. Now there's a little activity here. It says complete this ray diagram by drawing 3 additional rays. You don't have to do it from, I said other nose. That's kind of funny. Nose, other nose, and teeth. Okay, how about this? Let's do her ear and teeth. So I'll do her ear for now. So what happens is, now this is going to be hard for me because the tools that I have to draw straight lines, let's see if they work. How do I draw a straight line using this software? Shapes. All right, let's try this. Okay, so let's try one coming from her ear. So the one coming, okay, see what I mean? That's annoying. Okay, so that's not going to work. Okay, anyway, you're gonna have to forgive me because this thing is not too sharp. I'll do my best. See how it snaps? That's so annoying. Forget it. Okay. So in other words, I drew a ray for you like this. You have to draw another ray from some other part of Robin's face going into Bridget's eye, okay? And then trace the virtual ray and everything else. So give it a shot and we'll take it from there, okay? So that's how you draw it. It's called a ray diagram. Now, her image has characteristics, okay? And the characteristics you can memorize by looking at this acronym called SALT, okay? And like I said, I don't mean to say Robin is salty. I know that that's an expression. What SALT means is size, S for size, A for attitude, so she might have a bad attitude, right? L for location, and I don't mean Ottawa, I mean she's behind the mirror, and then type, okay? Now let me explain. What do these four characteristics mean? So size is obvious, okay? So size is the image bigger, smaller, or the same size as Robin? Now on a flat mirror, it's the same, okay? So I'm just going to write bigger, smaller, or same. Now in the case of a plane mirror, it's the same size. So in other words, when you're looking at your reflection in a flat bathroom mirror, you look the same size as you look all the time to everybody, right? All right, attitude. So for Robin, we'll just say bad, right? No, I'm just kidding. Attitude just means, is she upside down? Is there any inversions? Okay, so here in a plane mirror, it's laterally inverted. So in other words, her left and right has switched in the mirror, you'll notice. Sorry, a laterally inverted. Okay. So flat mirrors have a lateral inversion. That means like if you're reading text on your shirt, like my shirt says Black Lives Matter, but if I look at the reflection of that in a flat mirror, it'll be backwards. You might have noticed that when you look in mirrors too. So it's laterally inverted, but it's vertically normal. So you don't look upside down in the mirror. It's only laterally inverted, so left and right. Okay. Location. Where is the image? Now in this case, for the plane mirror, I keep writing that because we're going to look at curved mirrors at some point. The image is behind the mirror. So in other words, it looks like you are standing in front of the mirror. It looks like it's behind the mirror, okay, your image. Now the type is real or virtual. Let me explain. A virtual image does not mean you're in virtual reality or it's a computer-generated image. Get that out of your head. The word virtual means like if you were to put a screen, okay, where you think you see the image of Robin, so behind the mirror, would you see her projected onto that screen? And the answer is no, the mirror is actually opaque, so you can't see her at all. So real or virtual? Real means you can see it on a screen, so a projector has to make a real image for you to see it on the wall or on a screen. Virtual, you can only see it through okay, I'm just trying to think how to phrase this. So a virtual image, you can't see it through the screen, but you must look through the device. So in other words, you can see your own image in a mirror, okay? In a plane mirror, your image is virtual. So you're looking at a virtual image of yourself. when you look in a flat mirror. Okay? You're looking at a virtual image of yourself. It doesn't mean VR this time. We were using this word virtual before computers were invented, you know. Okay? And that's it. All right. So moving right along. Okay, now you understand the characteristics of an image. I do have a Mira activity for you. Now, you might not have a Mira, and it's M-I-R-A, not mirror, but a Mira. Okay, and you're going to have a hard time with this activity if that's the case. But why don't we save this, and we'll do it first thing in class the next day. I have a little device that you need to use, so you can't do this right now. So let's save this for, what, Thursday? And that's it for today, guys. So anyway, I know it took a little while, 50 minutes, but you know what? You've had very little to do with me, like at home so far, especially lately, okay? Like maybe early on we had a few things to do at home, but not anymore. And so it's been a little bit of a break for you. I just spilled my water on a bunch of documents. That's wonderful. Hey, at least it wasn't your test. Okay, so yeah, save that one for tomorrow. All right, guys, so have a good day, and I will talk to you on Thursday. Okay, talk to you soon.